All right, guys, here is open response question number 3 from some previous AP exam. I forget what year. We've got a table. So this is what I would call a table problem. Like I've said, there are lots of these on the exam. It says the twice differentiable function W models the volume of water in a reservoir at time t, where W of t is measured in gigaliters and t is measured in days. The table above gives values of W prime of t sampled at various times during the time interval t between 0 and 30. At time t equals 30, the reservoir contains 125 gigaliters of water. And part A says, use the tangent line approximation to W at time t equals 30 to predict the volume of water W of t in gigaliters in the reservoir at time t equals 32, and show your work. So the idea is that we'd like to predict W of 32, right? They're asking us to predict the volume of water at time t equals 32. So we'd like to predict W of 32. The way to do that is to, as they say, use the tangent line approximation to W. The tangent line approximation, just to remind you how it goes, here's how it looks. We don't know what the function W looks like, right? We don't have a formula. We don't know what it looks like. But here's what we can do. At 30, let's say that 30 is right here. If we can find the tangent line at 30, which is what they're telling us to do, then we can use that tangent line to predict the value of W at the nearby time 32. So the overall plan is construct the equation of the tangent line at 30, then use it to approximate W at 32, which would give us the y coordinate of that point there, which of course is close to the actual value of W at 32, which would be here. How does it go? Well, whenever you're trying, first of all, the tangent line approximation, it's nothing more than using the equation of the tangent line. So what we have to do is write down the equation of the tangent line. To do that, you should always start by writing down point slope form, which is y minus y1 equals m times x minus x1. The x1 and y1 are the coordinates of the point on the line, which would be this point right here. Obviously, the x coordinate, technically it's a t coordinate, but whatever, the horizontal coordinate is 30. What is the y coordinate of this point? Well, you wouldn't know if they hadn't told you earlier in the problem that at time t equals 30, the reservoir contains 125 gigaliters. That's really just telling you that W of 30 is equal to 125. So that's the y coordinate of that point. So that's going to be your x1, that's going to be your y1. That takes care of this and this. To finish writing down the equation of the tangent line, the only other thing we need is the slope m, which is of course the slope of the tangent line. Normally, what you would do to find this is you would plug 30 into the derivative of W, but we don't really have a formula for W. Instead, what we have is a table showing us some values of W prime. But we can figure out, we know what W prime of 30 is just from the table. W prime of 30 is 0.5. So that's the slope of the tangent line at 30, which is the slope of the line whose equation we're trying to write down. So that's your m right there. If you plug all of that in, we have y minus y1, which we said is 125, equals m, which we just said is 0.5, times, it's x, although actually the independent variable we're using here is called t. Maybe I should call it t. T minus x1, which is 30. And that's the equation of the tangent line. Now, if you want to use it to predict the volume of water at time 32, what that means is you're going to replace this T right here with 32. And that gives us y minus 125 equals 0.5 times 32 minus 30. That's ultimately, if you now solve that equation for y, what is that going to give you? 32 minus 30 is 2, times 0.5 is 1, and then you would add 125 to both sides. So that gives us 126. So that is the approximation in gigaliters. Okay, so that is part A. Part B, let's read part B. It says, use a left Riemann sum with 3 subintervals indicated by the table in the data to approximate the integral of w prime of t dt. Use this approximation to estimate the volume of water w of t in gigaliters in the reservoir at time t equals 0. Show the computations that lead to your answer. So let's begin by doing as they suggest. We'll approximate this integral using the table data and a left Riemann sum with 3 subintervals. So what are those subintervals? Overall, as I've said in many times, whenever you're doing a Riemann sum, I really encourage you to draw a picture. Our interval goes from 0 to 30. We don't know what w prime looks like. Really, it's just some curve. But we have this table data, 0, 10, 22, 30. If you plot those values, you'll see that it creates 3 subintervals. So 10, 22, and then 30 is already on there. So as you can see, we have 1, 2, 3 subintervals. So above each of those subintervals, you're going to construct a rectangle. How high is each rectangle? Well, they tell us to use a left Riemann sum. So the height of each rectangle is determined by the value of the function that is w prime at the left endpoint. So this first rectangle, its height is going to be w prime of 0, which is 0.6. So 0.6 is the height times the width is, of course, 10. Plus, then you've got another rectangle here. Its height is determined by the value of the function at 10, which is 0.7. So that would be 0.7 times the width of this subinterval. Be careful, the subintervals are not equally sized in width. So this is actually 12 units wide. Plus this last subinterval, it's determined by the value of the function at 22, which is 1. So that's 1 times the subinterval width, which is 8. So what is this exactly? I think that this would be 6 plus 0.7 times 12 would be 8.4. And then 1 times 8 is just 8. So I think this winds up being 22.4. So that is approximately the value of the integral from 0 to 30 w prime of t dt. Of course, that's actually not the answer to the question, because they say use that approximation to estimate the volume of water w of t in gigaliters in the reservoir at time t equals 0. So we want to approximate w of 0. How can you do that? Well, the idea here is, you know that w of 30 is 125. They tell you that at the beginning of the problem. The reservoir contains 125 gigaliters at 30 units of time in 30 days, I guess it is. Well, this figure here, what is it telling you? The integral of a derivative gives you the net change. So this 22.4 is the net change of the amount of water in the tank over this time interval. So from day 0 to day 30, the tank increases in volume by 22.4 gigaliters. And at the end of that time period, there are 125 gigaliters in the tank, which means that originally at time 0, the number of gigaliters is just 125 minus 22.4. So W of 0 is going to be about 125 minus the 22.4. And as I've said, you can leave answers unsimplified on the AP exam, but if you wanted to, I guess this would be 102.6. I believe that works. Yeah, but you can just leave it like that. Oh, and you should write the units. That's a good habit. So that's part B. Part C says, explain why there must be at least one time t other than t equals 10, such that W prime of t is 0.7 gigaliters per day. Right away, I can tell this is some kind of theorem, maybe the intermediate value theorem, or maybe the mean value theorem. Those are the theorems that say things like, the function must take on this certain value at some point. That's kind of the flavor of those theorems, and I'm sure that that's what we're supposed to use here. Now, what exactly can I say here? Well, if you think about it, W prime 10 days in is equal to 0.7. And if you look at the following values, it's going to have to equal 0.7 again later on, because at day 10, it starts at 0.7, then it goes up to 1, and then it comes back down to 0.5. And that means that during this time interval between days 22 and 30, at some point, it's going to be equal to 0.7, because 0.7 is between these two values. Now, that's not a very mathematically rigorous argument. There are some assumptions built in there, and there's actually a theorem that I'm using here. There's kind of a lot going on. So first of all, you'll notice they tell you that the function is twice differentiable, okay? So if we're going to be really formal and rigorous, what I would say is W twice differentiable means, what does that mean? It means you can differentiate it twice, which of course means that W prime is differentiable, right? You can take the derivative of the derivative. That's what it means to be twice differentiable. You'll remember that, or hopefully you'll remember that differentiability implies continuity. So if a function is differentiable, it is automatically continuous. So because W prime is differentiable, that means that W prime is in fact continuous. And that's important because it means it satisfies the conditions of the intermediate value theorem. The intermediate value theorem says if you have a continuous function over an interval, then that function will take on all intermediate values. Since 0.7 is an intermediate value, between 1.0 and 0.5, and W prime is continuous, the intermediate value theorem says W prime must equal 0.7 at some time between t equals 22 and t equals 30. So that is a fully developed argument. I think that if you just said intermediate value theorem and 0.7 is an intermediate value, I think that you'd probably get some credit. But technically, to know that the intermediate value theorem applies, you have to know that W prime is actually continuous. And knowing that W prime is continuous requires that you make this observation here. If you neglected to make this first observation, proving that W prime is continuous, I think you'd probably lose a point or something, but you'd probably still get some credit. Finally, let's look at D. It says the equation A equals 0.3 W to the 2/3 gives the relationship between the area A in square kilometers of the surface of the reservoir and the volume of water W in gigaliters in the reservoir. Okay, so there's a relationship between the surface area A and the volume W. Find the instantaneous rate of change of A in square kilometers per day with respect to T when T is equal to 30 days. What they want here is they want the instantaneous rate of change of A. That's dA dt, the derivative of A with respect to time. And they want it specifically at T equals 30 days. So what can we do? This is basically a related rates problem. Not rate in, rate out. Don't be confused. It's not rate in, rate out. It's related rates. What we have is a relationship between A and W. And I can take the derivative of both sides of that equation with respect to time, because they're both functions of time. They're both changing over time. If I do that, I get dA dt equals, well, taking the time derivative of this guy, W is a function of T, and 0.3 W to the 2/3 is a function of W. So really the right-hand side is a function of T, which means you're going to have to use the chain rule. The outside function, I would say, is 0.3 blank to the 2/3. So the derivative will be 0.3 times 2/3 blank to the -1/3. That's the derivative of the outside function. What goes here? Just W, the original inside function, times the derivative of the inside function, which is dW dt, the derivative of W with respect to time. You could write W prime if you wanted, that's fine. So you want to find dA dt when T is equal to 30, so you just need to evaluate the right-hand side at 30. That's pretty easy to do because, so 0.3 times 2/3, W evaluated at 30, we know what that is. W of 30 is 0.5, right? Or no, sorry, that's W prime. W of 30 is 125. We're told that right at the beginning. So that's 125 to the -1/3 times dW dt. Well, that's W prime at 30. And at 30, we already observed from the table, that's 0.5. So times 0.5. So that would be the answer there. Again, the units are square kilometers per day. I don't think we have to simplify this. It doesn't say to, so I don't think that we need to. But if you wanted, then, well, I don't know, simplifying this is a little bit annoying, but not too bad. 125 is a perfect cube, so you actually could simplify that. But anyway, why bother? This is good enough. Okay, so that is that. Let's now move on to a different open response question. Let's move on to number 5 from the same year. I forget what year. You'll see these a lot as well. So let's have a look at 5. It says the graph of the continuous function f consisting of 3 line segments and a semicircle is shown above. Let g be the function given by g of x equals the integral from -2 to x f of t dt. So g is an integral function. You're integrating f. F is the function graphed here. So it says find g of -6 and g of 3. Well, g of -6, just using the formula directly, would be the integral from -2 to -6 f dt. Now, this makes me worried because the lower limit of integration should be less than the upper limit of integration, right? In order to understand what the integral is actually talking about, you really should have the lower limit be less. So I'm going to switch the 2 limits of integration. Doing that, of course, produces a minus sign. So it's going to be the opposite of the integral from -6 to -2 f dt. This integral here, that is just the area under the graph of f from -6 to -2. Of course, you don't have a formula for f. You can't find an antiderivative, but you don't need to, because the area under this region here is just a triangle, and we can use geometry to find the area of that. The area of this region, it's a triangle, so the area is 1/2 base times height. It's 1/2. The base is, well, from -6 to -2 is 4. And the height, you can see that the y coordinate of this point is 5. So the height is 5. So that's 10. Of course, we have a minus sign in front of our integral, so that's actually -10. G of 3, just using the formula, again, that's the integral from -2 to 3 f dt. There's no need to flip the limits of integration here because the lower limit is already the lesser number as required. This is just the area under the curve from -2 to 3. Although actually, we should be careful. It's technically the signed area under the curve. That's what an integral gives you. So what this integral is going to do is it's going to count the area of this semicircle here positively because it's above the x-axis. But then this little triangle here is going to be treated as negative because it's below the x-axis. So let's find these areas. The area of the semicircle is 1/2 pi r squared because it's half of a circle. So 1/2 pi r squared. What is r? It looks like it's 2. So times 2 squared, which is 1/2 times pi times 4. So that's just 2 pi. And then this little region here, the little triangle below the x-axis, it's 1/2 base times height. The base appears to be 1. The height appears to be 2. So simplifying all of that actually just gives us 1. But of course, in the integral that we're considering here, that region is going to be treated as negative. So the total integral is going to be 2 pi minus 1. So that's g of 3. Part B says find g prime of 0. So you need to find the derivative of this function and evaluate it at 0. Well, this function is an integral function. And the second fundamental theorem says when you have an integral function like this, its derivative is obtained just by taking the x and putting it there. G prime of x is nothing more than just f of x. If you remember, technically, in order to use the second fundamental theorem, your integral function needs to be of a particular kind. Namely, the lower limit of integration needs to be constant, and the upper limit of integration needs to be just a plain old x. But that's exactly true for this function. So that's a pretty easy one. We've done harder ones than that. So the derivative of g is just f, which means g prime, so that's by the second fundamental theorem. So g prime of 0 is just f of 0. And what is f of 0? Well, we have a graph of f right here. F of 0, you can see, is just 2. So that's 2. That's all done. Part C, find all values of x on the open interval -6 to 3 for which the graph of g has a horizontal tangent. Then determine whether g has a local max, local min, or neither at each of those values. Justify your answers. Horizontal tangent means that the derivative is 0. So we want g prime to be equal to 0. As we discussed on the previous page, g prime is actually just f. So this amounts to asking when is the function f equal to 0, which can be found by looking at the picture. F is equal to 0. Well, actually, it's equal to 0 at -6, but if you notice carefully, they exclude that from the interval of consideration. See how they're looking for x strictly bigger than -6 and strictly less than 3. So we don't need to include -6. It's outside the interval that we're considering. However, -2, certainly. So from picture, we have x is equal to -2 and also +2. And again, technically, f is equal to 0 at 3, but that's outside the interval of consideration. So that's the only thing. Those are the only places where f is equal to 0. So if you do a sign analysis for f, you can then determine whether each of these guys is a local min or a local max. These are, of course, critical points of g. They're places where g prime is equal to 0. So f, which of course is the same thing as g prime, here's a sign analysis. All right, on this interval here to the left of -2 is f positive or negative? Well, from the picture, you can see that to the left of -2, f is definitely positive. Between negative and +2, again, f is positive. And then past 2, f is negative. So what we can conclude is that this is neither a local min or max, because the derivative of g is increasing both before and after. On the other hand, what's going on here, g prime is positive and then negative. That means the original function g is increasing then decreasing, which means that you have a local maximum. And that means g prime, that's happening because g prime is positive, then negative. So when they say justify your answers, this kind of thing is perfectly acceptable. You don't need to write an essay, full sentences are not really required, but just something to show that you understand why. Finally, part D, and this is where we'll end. Find all values of x on the open interval -6 to 3, so same interval as before. Find all the values x for which the graph of g has a point of inflection. Explain your reasoning. So point of inflection, that's of course a place where the concavity changes. It's always worth remembering and emphasizing that concavity can be understood at many different levels. If we're talking about the concavity of g, maybe I shouldn't write this here because I don't want to include this as part of my answer. But just to remind you guys how it goes, g concave up. What does that mean? Well, at the level of the original function g, it means that the graph of g looks like this, happy face. At the level of G prime, it means that G prime is increasing. At the level of G double prime, it means that G double prime is positive. And you can use whichever of these levels is suitable. G concave down obviously just means the reverse of all of that. Therefore, an inflection point is any place where you go from here to here, from happy face to frowny face, or from G prime increasing to decreasing, or G double prime positive to G double prime negative, or the other way around. Now, which level of analysis you should consider just depends upon what information you've been given. In this picture here, we have a graph of f, but of course, if you remember, f is actually the derivative of g. So what you have here is a graph of g prime. This is g prime. So I think that we should consider it, we should analyze the concavity at the level of g prime. You'll have an inflection point anytime g prime, this graph, switches from increasing to decreasing or the other way around. Again, we're excluding the points -6 and -3. We're just considering the interval between those two values. So I see certainly G prime switches from increasing to decreasing here. So G prime switches from increasing to decreasing at, where was that? I guess at -4. So that is one point of inflection. And it switches from decreasing to increasing at -2. And from decreasing to increasing at -2. And I think that's it, because, or no, that's not it. Right here at 0. G prime switches from increasing to decreasing. And from increasing to decreasing at 0. So those are the 3 inflection points. And that's the end of the problem. So, okay.